Hey there, guys. Welcome back. How's it going, Gary? Good to see you. Welcome, one and all. We'll be starting in about 2 or 3 minutes. I'll be right back. I'm just going to grab my glasses, so hang in there. Thank you. Hey there, Alexandra. Good to see you. Got a few of us here already. That's always nice. Anybody else? Feel free to say hi. Hi, Haley. Hey, Rachel, and hey, Andrea. Good to see you guys. Just another minute, pretty much. Good afternoon, evening, whatever time it is. Some of you are probably watching this later in the middle of the night or whenever you're watching it. So wherever and whenever you're doing this, welcome back. Interesting week with the elections going on, all kinds of things to keep us distracted in a way. But it's an interesting time period, I guess, to be an American and to be alive. So a lot of us, I'm sure, got a chance to vote. I certainly did, and felt good. Welcome back. Yeah, we would love to see them finish the counts. I think tonight, at least one of those two states will probably be done. It's the volume of mail-in ballots, I guess. They take a little longer to verify each one because you have to match the signature. You have to, sort them. So patience is key. We'll get it done soon. No, we've got to count everything. Obviously, we all voted, and that's democracy. So the people get their way. All right, guys, welcome back. Thanks so much for being here. So I, had a thought to give you guys the Tuesday off so that you could vote. And, at 5:30 to 6:45, that's kind of close to when the polls close. And I just thought, within an election like this, I don't want to ever look back and think, oh, maybe there were certain students that wanted to vote and my class made it difficult for them. So that was my main motive, to give a substitution for the Tuesday meeting. But I'm a little disappointed in myself because I think the video that I sent to you, I've been notified and I've kind of looked into it. Have you guys noticed that there's an issue with viewing it? Can anybody please verify or confirm? Tell me if any of you have tried to. What was the situation with that? Is it, say you have to purchase it and you have to pay for it or something? Let me know. Yeah, you have to pay for it. Yeah, so it didn't work. Okay, well, I'll try to find an alternative means by which you could view the same thing. See, I actually purchased that, and it's in my YouTube purchases. So I thought, because I'm the owner, that I was able to link to it and you'd be able to view it that way. But yeah, it didn't work. So not to worry. I'll be able to inform you on the same information. It's kind of a fun video, though. I always used to show it in the classroom because obviously with the classroom technology, I could just, hit play and pull down the projector, and we could all just watch it using my login and stuff. But I guess that's not the case with this particular video. So I'll have to find, what I will do? I'm just going to find alternative videos with the same content, something that's on YouTube that definitely does not have a paywall, and I'll send it to you over the weekend. So you'll be able to get it in at a later time. But anyways, we are now going to start talking about that type of topic. So quickly, I'll just summarize where we've been and where we're going next. We start off the semester, we're talking about the philosophy of religion and various arguments for and against the existence of God. Then we studied ethics for a while, the theory of morality, what's right, what's wrong, what are the different approaches that some very important authors have had to that topic, utilitarianism, Kantianism, and applying those theories to some ethical dilemmas like the trolley problem or the case of global poverty. And then we looked at epistemology most recently. We studied what it is for a person to have knowledge, what is the ancient Greek account of that, or on the other hand, what is truth, justification, belief, how did Gettier challenge that classical definition, and then what did Descartes have to say about the possibility of having certainty. That was our most recent lecture, and basically, his conclusion is that if you use the method of doubt to find certainty, that means assume to be false anything that could be false, then that will leave you with almost nothing. Nothing from the sense perception could be trusted 100% because it could be an illusion or dream. Also, even knowledge from math and logic could be false if there were an evil demon manipulating you, but he says you can't doubt that you exist because you're thinking in the first place. So one thing that cannot be doubted, which is totally certain, is the existence of you, at least your mind, with regard to your body. I don't know, all bets are off about that because it's something you perceive with your five senses, but the fact that you're thinking does verify and prove that you have consciousness, so you exist. Okay, now, as we continue the course, we're going to start talking about another major branch of philosophy. So philosophy has ethics, philosophy of religion, epistemology. Another big subject area that is a focus for some is called metaphysics. Okay. Okay, so metaphysics is it's a very broad concept, but it really just refers to a deep investigation into the nature of reality. Oh, you said you tried to email me 3 times and it gave you a delivery error? I'm just not so sure why. What email address are you using? Really? Well, both of you then. Let me stop this for a minute. Rachel, Red Panda, when did you send me the email? For the midterm score, okay. Well, how did you send the message? Did you send it by hitting reply to the Canvas notification, or what did you do? Did you go to compose an email and then type in my email address like you should? Tell me the steps that you took. Okay, you're not supposed to do that. You can't do that. That doesn't send. You have to compose an email. You have to click create email and then just type in my email address. You say you tried both. Okay, how about this? Let's just do a little experiment. Are you guys with me? Okay. I want to clarify your issue really fast. Okay, so what I've done right now is I'm logged in to my email account, all right? And, okay, so I'm logged in right now. And I'll see when you send me the message. So how about right now, you attempt to send it to me? What? Okay, how about this also? You guys, can you type in this chat what you think my email address is? Go ahead. Or you can go to your sent messages in your sent folder, and please look at the exact spelling. Copy and paste that and put it here. rvulich@fullerton.edu. Well, I mean, I've answered a lot of other emails from students about their midterm grades and stuff. So, okay, how about this? Let me say this to you. When did you send that message? Did you send it to me on election day? Is that when you did it? Go ahead right now, and send me just any test message using that email, using your Fullerton account. Yeah, Tuesday, email was down across the country. And the reason is because of the election, guys. So, Damien, is that who's emailing me right now? Damien, let me know. Who's Damien? There you go, I'm getting your message. Seems like there's no problem. Daniel, who's that? Daniel, where are you? I'm getting another message. There you go. Thanks, Danny. I got your message. Okay, now Rachel. Rachel, you sending me a message? It's right there. I'm getting your messages. There's no problem with that. You got to be a little bit more persistent. Try and send me the message under different Wi-Fi conditions. I don't know, but that's all you. I mean, you gotta send me the message and make sure that the delivery comes through. There's no problems with my email address. There's no problems with my ability to receive messages because I'm answering hundreds of them all the time. But I did notice this, okay, that on the day of the election there was a problem. Now, Damien, you're telling me that you tried to do it on the 31st and the 1st. I can't speak to that. I really don't know. But many of the others that are here did send me their questions about their midterms, and I've responded to each one. So just send me another message, I guess, because I've got those. I see Rachel, Daniel, Damien have just sent me emails. Okay. The internet was down on Tuesday, so there could have been some of you guys that, I don't know if your memories are correct or incorrect, but you might have tried to send me something on Tuesday. Okay, well, I'm telling you that if you try to send me something on Tuesday, it didn't get through. Damien, I don't know, you might have a messed up computer or something, but you have a different case if you deny that you tried to send it on Tuesday. Yeah, I guess it's weird, but thanks for letting me know. All right, back to the lesson now, okay? Metaphysics. What is metaphysics? Metaphysics is just a deep investigation of reality. What's the nature of reality? What things exist? So, originally, this is a phrase that was coined by the ancient Greek philosopher Aristotle, and he intended by it just to go beyond the physical, beyond physics, metaphysics. But since then, it's kind of taken on a slightly different meaning, and it just refers to any kind of deep, focused inquiry, investigation into fundamental aspects of reality, like, I don't know, do we have human free will, or are we just determined to act in the way that we do? How does an object remain identical over time? For example, maybe some of you have heard that every cell in your body is completely recycled, I think, every 7 years or so. So you sitting there in this chair that you're in right now, you don't have any of the physical parts in common with photos of you from 10 years ago, but yet you're the same person. How does an object remain identical over time? What is the nature of properties or objects? Well, another important metaphysical topic of inquiry, and the one I've chosen for us to look at, is time. What is the nature of time? What's going on with time? What is the current best physical understanding of time? What's the scientific consensus view of it? What are the difficult aspects of trying to think about it when you investigate it beneath the surface? So we are looking at the metaphysics of time for the next couple of meetings. And something that we're all familiar with, time, you know, we live according to the clock. We all know when things are going to happen, how long they take, how much time things have taken so far, how much more time we have to live, to work, to do whatever it is. Right now you're here because you know that this class is from 5:30 to 6:45. So time is a fundamentally basic part of all human life. And that means that a lot of times we're just it's something that we just take for granted. We don't kind of ask deeper questions about it. But we should think about it in a deeper way, because it's actually quite hard to fully comprehend it once you start to do that. So we're going to begin, though, with the work of this man, Albert Einstein. Okay, Albert Einstein, and we all have heard his name, I'm sure. He's the famous, world-famous physicist, scientist, philosopher who discovered the theory of relativity, the general and the special theory of relativity. You know, he published these Nobel Prize-winning papers in physics when he was a very young man, just in his young 20s, working as a clerk at the patent office in Germany. And from that position, you know, on his free time on the side, reading papers in physics and writing these detailed proofs, he was able to prove fundamentally revolutionary things about space and time that to this day we still regard as proven and correct. So he's a huge monument to the academy, to the intellect. He lived from 1879 until 1955. So he wrote these groundbreaking papers on the electrodynamics of moving bodies in, I believe, 1906 as a young man. And then 10 years later, in 1916, he wrote a book called Relativity. And the goal behind that book from 1916 was to try and bring down to earth a little bit some of these heady concepts that he had written about in a more technical way before to a smaller audience of, you know, mathematicians, scientists, physicists. He wanted to bring those ideas into the broader mainstream so that more everyday people could think about them and understand them. So he tried his best in this 1916 book, which is a great book. I'll recommend to anybody if you're interested in physics and science. Einstein's relativity book from 1916. Again, it's trying to reach a wider audience. It's trying to make these ideas a little bit more digestible for the average citizen. So that's the book. And from that book, our textbook that we all have took a small section away from it and printed it, and they gave it this different title. So that I'll put on the board now. So from Einstein's 1916 book, Relativity, we're looking at this little section, and the title of it is Time and the Relativity of Simultaneity. Okay, there you go. Oh, and let me just say this, by the way, because I don't want to let this go. When we were talking about emails and stuff, everybody feel free to email me for the scores that you want, if you want them on your midterm, your first essay. Those things have been graded. And in the message that I sent around, I was saying I provide grades to any student per request. When you request it, you're going to get the grade with a detailed set of comments. So, but you got to ask for it. And if you do, I'll get you a reply within a day or 48 hours at the most. So just a reminder, midterms, everything's all graded. The next paper topics I'm going to assign in about a week. But between now and then, if you want your scores, just let me know and I'll get it back to you over the weekend if you do ask. Okay, so Time and the Relativity of Simultaneity by Einstein. So Einstein is famous for revolutionizing the modern day understanding of time and space. Before him, the dominant paradigm in physics was Newton, Isaac Newton, and Newton's laws. But Newton believed that when it came to time and space, that they were separated, or that they didn't have any relationship to each other. Newton's belief, or his theory, was that no matter how fast or how slow an object moves through space, that had nothing to do with the rate of time passing. So Newton thought that a thing could be moving fast, slow, standing still, or anything in between, but it would never have any effect at all on the passage of time, that time would just continue moving at a constant rate in this sort of linear direction, and nothing could ever speed up or slow that down, and it was always just universal and unrelated to the movement aspect or the velocity of objects in space. But what Einstein was able to show is that that's not actually true, that time and space are not separate, but that they're integrated into one common structure called space-time. And what space-time theory implies is that how fast or slow an object is moving through space, its state of motion, its velocity, does in fact affect the rate of time passing relative to other objects in space with different state of motion. So this, once you start to understand what it actually implies for us and for our place in the universe, it's quite deep, it's almost trippy and very, very weird, but I'm going to try my best to get you guys to that understanding. So we're taking our little crash course into the theory of relativity and Einstein's physics. Okay, so let's begin. Starting off, what he says is, suppose the following. So Einstein says, I want you to imagine this scene, okay? We have a railroad, like a railroad track. Oh, hey, Peach. Okay, we got a railway embankment there. That's what this line represents. And on this track, on two separate points, let's say that there's lightning strikes that occur. So one is here, and then there's one over here. I've labeled the two A and B. Okay, so you got lightning strike A to the left, and lightning strike B over there to the right. Now, question, or I guess statement. Suppose now that these two lightning strikes happen simultaneously. Okay, suppose they do happen simultaneously. So, if they happen simultaneously, here's what at least first seems to be a simple question, straightforward question. I'm asking you this, just this is all. What does that mean? What does it mean that the two lightning strikes are simultaneous? And Einstein says that it seems like it's an easy question to answer, but after a moment of reflection, you'll realize it's not so easy to answer the question as you might have thought, because any attempt to define simultaneous is going to pretty much be circular. Like, it's hard for you to say what simultaneous means without just saying same time as, which is elliptical for the word simultaneous. Can you try to do that? Can anybody attempt a definition of simultaneous? Like, if these are two lightning strikes that are simultaneous, what does that mean, in other words? And don't use the word simultaneous, and don't just say, you know, at the same time, because that would just, we'd have to ask, well, what does it mean that they happen at the same time? But do you have any ability to try and supply some answer to that question? What does simultaneous mean? Well, yeah, that's probably is what you were going to say, right? That just means at the same time. But look, that's not at all, you know, a disrespect to you, because Einstein, the great genius Einstein, says, yeah, it's really hard to define. It's not so easy as it seems at first. I see you, Andreas, saying things occurring at the same perceived moment. That's pretty good. But I mean, you know, I could, if I really wanted to be picky, say, well, at same moment, and same moment is same time. So the two things happen. I like you got perception in there, though. That's actually big, and that's going to come into play as I describe Einstein's own answer. Well, at any rate, and Gary, I see synchronicity, very good high-level vocabulary term. But yet again, and it carries other associations, synchronicity, like it's almost sometimes thought of as like providential or sublime, that two strange things are happening at the same time. Brooklyn, they happen during the same moment on a chronological timeline. Another very good, noble attempt. But it seems like all of these attempts kind of revolve around a similar cluster of ideas, that it's happening at the same moment, same time. So Einstein says this now. He talks back. He says, okay, so it's not so easy to define. And he then claims, okay, some people who hear my question, they might just throw up their hands and be like, come on, do we really need to say what it means? Who cares? At the end of the day, everyone kind of knows what it means, or at least even if we can't say in a specific definition what it means, we don't have any trouble getting around using the word. Like if I say, hey, I want you to like start running simultaneous with me, okay? Ready, set, go, and then we go. It's like the other person wouldn't be looking back and be like, huh, what do you mean simultaneous? I can't understand that. So you could argue that, is a definition really strictly necessary if we're able to use the word and if we kind of understand what it means? Can't we just sort of deny giving any answer and just wave our hands and say, come on, it's clear enough even if we don't have a precise, detailed definition? Well, Einstein says, no way, I don't accept that. Because he points out that if you're a physicist, a scientist, and even if you're not, you can't be operating with undefined concepts. So we can't be out here saying simultaneous, but I don't really know what it means. He says we have to have a definition and an explanation of it that is so clear and so precise that we could actually conduct an experiment to see if the two events were simultaneous or not. And he says if we don't have a definition of it that can be tested to verify or disconfirm whether the two events were simultaneous, in other words, if we don't know how to test for this proposition, then we might be using a word that doesn't even have a definition or a meaning. Like we might be just kidding ourselves that it actually means anything at all. So he then says, I need a definition that is so clear and sharp that we could use it to do a test and test the question physically. So let me read that. You'll hear Einstein. Don't take it from me. Here's Einstein talking. So he says, lightning has struck the rails on our railway embankment at two places A and B, far distant from each other. I make the additional assertion that these two lightning flashes occur simultaneously. If I ask you whether there is meaning to this statement, you will answer my question, yes. But if I now approach you with a request to explain the meaning of the statement more precisely, you find after some consideration that the answer to the question is not so easy as it appears at first sight. After some time, perhaps the following answer would occur to you. Okay, now he's speaking in the voice of this imaginary critic of the question. Someone might say, the significance of the statement is clear in itself, and it needs no further explanation. Now, of course, it would require some consideration if I were to be commissioned to determine by observation whether in the actual case the two events took place simultaneously or not. And Einstein then says, I can't be satisfied with this answer for the following reason. Suppose that as a result of ingenious considerations an able meteorologist were to discover that the lightning must always strike the places A and B simultaneously. Then we would be faced with the task of testing whether or not this theoretical result is in accordance with reality. We encounter the same difficulty with all physical statements in which the conception simultaneous plays a part. And here's a key quote. The concept does not exist for the physicist until he has the possibility of discovering whether or not it is fulfilled in an actual case. We thus require a definition of simultaneity such that this definition supplies us with the method by means of which we can decide by experiment whether or not the lightning strikes occur simultaneously. As long as this requirement is not satisfied, I allow myself to be deceived as a physicist, and of course, even if I'm not, when I imagine that I am able to attach a meaning to the statement of simultaneity. And then he says, I would ask the reader, don't proceed any farther until you're fully convinced on this point. So he's saying to you, we can't have a vague, ambiguous, unclear definition of simultaneous. We've got to have it so precise and clear that we can actually go out and test this in the field and see whether it is simultaneous using a test. So the question now kind of becomes, what could be the test method that we could utilize to determine if these are simultaneous or not? So now Einstein says, let me tell you what the test would be. So here's this proposed test that Einstein mentions that's going to be used to see, are these two events simultaneous or no? Okay, let me erase the title up here. We don't need that anymore. So here is the little test. Let's measure the length between these 2 points, A and B, okay? Now that creates a line segment, the line segment AB. Okay, question everybody, back to geometry if you studied a little of that, or even if you didn't, I'm sure you can understand. Would there be a midpoint in the line segment AB? Would there be one? Does this line A to B contain a midpoint? That's a straightforward yes or no for you. What do you think? Is there a midpoint on the line? Don't overthink it too much. It's not a trick question. But someone still has to answer it, so tell me. Yes, of course there is. What's a midpoint, everybody? Well, it's the point that bisects the line. So that means that there's an equal distance between A to the midpoint and B to the midpoint. So, I'm sorry, Peachy. She just wants so much attention, but I gotta move her to the next room. Come on, girl. Over here you go. All right, guys, sorry. You know, I love it when she's here during the lectures, but sometimes she is more calm and other times she's more in my face. So anyways, yeah, back to this, the midpoint. Here it is, M. Oh, man. Peachy. I thought I had her in the other room, but I didn't fully close the door. 1 second. Come on, girl. Come on. All right. The midpoint, M. There it is. So now, let's just position an observer here at that midpoint. So it's this guy. Right there, at the midpoint M. So this man or woman, whoever, is in the middle of A and B. The distance between A and M is the same as B to M. That's why it's the midpoint. Okay, so let's make sure that this observer here is able to see the 2 points on the rail track in one field of vision, meaning that he has to be far back enough, basically, so that he doesn't have to like look left to right to see them both in the same visual field. Why do you think that is important, that he has to be far back enough so that they're both in the same frame of his vision? I mean, just visualize that, think about that question. If he's too close and he could only see one at a time, and then could he test this question of whether they're simultaneous or no? Why is it important that he's backed out enough so that he can see the 2 things in one visual field? Just making sure you can comprehend this description. Let me know. Or is it incomprehensible? Okay. You say no? I mean, think harder. He's standing far back enough so that he can see the 2 things in one visual field. If he was too close up and he could just see A, then he would not be in a position there to determine if the 2 events were happening simultaneously. Because suppose that he's looking at A and he sees lightning go off right there. And then he quickly, because he's too close to it, he shifts his gaze over to the right so he can look at B. And he sees lightning going off there. That's 2 subsequent moments because it takes a little time. There's a time lag between the moment of him turning his head to cast his gaze on the second point. So that can't verify simultaneity either way, because he's looking at the things in a sequence instead of in one visual field. So we got to make sure, in other words, that he's backed out far enough to look at them both in one field. Or if he is too close, then we've got to, provide him with some type of like mirrors that are inclined at 90-degree angles, and he can just use those to view the 2 points, okay? So, yeah, so we can see both happening simultaneously. Now, if he's at that point, which is just in between A and B, and if he receives the 2 light signals in his eye, so he sees them in one and the same visual perception, then we could define them as simultaneous, but only if we add one further stipulation, okay? Now, for me to talk about this next little point of the article, we got to think for a brief moment about how does vision work, okay? How does vision work? Is it magic? How is it that you're able to even see the screen that you're looking at right now? Like, what's the physical explanation of that? How is this screen even showing up in your vision? How does vision work? Well, I know there's a lot of details there. Let me ask it a different way if I can. Or if you want, you can go ahead and throw something in from that previous question and I'll see it. But let me also ask this. And this is very simple. Tell me, if you close your eyes right now, like if you shut your eyes, will you see anything? Will you see the screen at that time? Or will it not be visible if you shut your eyes? Okay, good, Andrea. Light being interpreted in the eye, yes. And by the brain, exactly. And if you do close your eyes right now, no, you won't be able to see anything in your field of vision. Why is that? Why is it that when the eyes close, you can't see the stuff? Well, it's very clear. It's because the light, the incoming light that would have otherwise struck your retina and then be processed by your brain for vision, is not able to reach when the eyelids physically, the skin of your eyelids covers the incoming light. So that's why you can't see things. Now, how you normally see is because the eyes are open and there are light rays. There are photons of light that strike the object that are then reflected off the object, and they are collected by your eyes, and then you see the image. So the reason that you're able to see stuff is because light rays that are bounced off of that object reach your eye, and they travel from the object to your eye at the speed of light. Okay, so if the speed of light is constant, meaning that it always moves at the same velocity from all parts of space to all others. So if the speed of light is the same speed from A to M as the speed from B to M, then we could infer that if they both reached this destination of point M at the same moment, they've traveled the same distance, and they've been moving at the same velocity, then that implies that they departed from their origins at the same time. It's kind of like one of those old math problems. Like, suppose that 2 cars both reach Pennsylvania at 2 o'clock, they were both traveling 60 miles per hour, and they both covered exactly 60 miles. Tell me the time that they both departed, and then you'd be able to deduce, reasoning backwards, that they left at the same time because they've arrived at the same endpoint. They've traveled over this, they've converged on the endpoint, having traveled the same distance, B to M, A to M, same distance, and the speed that the 2 things have traveled has been the same. Now, if we thought that the speed of light was variable, like the speed of light from A to M was twice as fast as the speed of light from B to M, then this could not verify simultaneity, you understand? Because in that case, even if the 2 light signals reached M at the same time, they would have departed at different points and then been non-simultaneous. Okay, let me give you an example here. Suppose that A and B are runners, like, I don't know, Alex and Betty, right? Now these are 2 runners of equal speed, and they're doing a race, and M is the finish line. Now suppose that they suppose that they both reach the finish line at the same point in time, like they both photo finish and it's exactly the same finish time. And they ran the same speed the whole way, right? And they covered an equal distance, like the start line to the finish line, they both covered the same distance, moving the same speed, and they reached the finish line at the same time. We could thus infer that they left the start line at the same time. But if one is twice as fast as the other, let's go through that scenario. Suppose that A is a runner who runs twice as fast as B, and they both converge on M at the same time when they finish the race. So if A is a factor of 2 twice as fast as B, but they meet at the finish line at the same time, in that case, who left first? The faster runner or the slower runner? If A is twice as fast as B, but they meet at the finish line at the same moment, then which of the two did depart earlier? The faster or the slower member of the race? You understand my question? Visualize that. Two runners meet at the finish line at the same time, but one was moving twice as fast. So the slower one had to have left earlier, yes. Because if he's twice as slow as this guy, and they're covering the same distance, but they move at a constant velocity and they reach M at the same time, that would have to mean that he got a head start. He was allowed to go halfway through, and then he started running at that point. And because he's twice as fast, he's able to close the distance, and they both arrive simultaneously at M, but they left at different times. Okay, so we can't have that when it comes to the speed of light, though. Otherwise, we could never determine that two events happen simultaneously. So we say then that A and B, the two light signals, are moving at a constant fixed speed, and there, by that stipulation, we get our definition of simultaneity. So the definition is basically, if there is an observer positioned in between the two events, and they're positioned in such a way that the light sources from the two events reach their eyes at the same time, then relative to that individual, the two events are considered simultaneous. Okay, now let me read a little of Einstein on this, and we can put all of the thoughts together. He says, after thinking the matter over for some time, you then offer the following suggestion with which to test simultaneity. By measuring along the rails, the connecting line AB should be measured up, and an observer placed at the midpoint M of the distance AB. This observer should be supplied with an arrangement, for example, two mirrors inclined at 90-degree angles, which allows him visually to observe both places A and B at the same time. If the observer perceives the two flashes of lightning in this position at the same time, then they are simultaneous. And then he talks about how we have to make the stipulation of the speed of light. He says, I'm very pleased with this suggestion, but for all that, I cannot regard the matter as totally settled, because I feel constrained to raise the following objection. The definition would certainly be right if only I know that the light by means of which the observer at M perceives the lightning flashes travels along the length A to M with the same velocity as along the length B to M. But an examination of this would only be possible if we already had at our disposal the means of measuring time. So below he just says that light requires the same time to traverse the path A to M as for the path B to M, is a stipulation which I can make of my own free will in order to arrive at a definition of simultaneity. So when you think about events happening simultaneously, you got to think about the receipt of the light signals to a standard observer occurring at the same time. And if the observer is positioned in such a way that the light signals that were emitted have traveled an equal distance, reached him at the same moment, and have moved the same velocity, then that would imply that they had departed from their respective positions at the same time. Using this definition of simultaneity, the receipt of two light signals from two events in one observer allows us to define simultaneity across the board, including how we use clocks to coordinate our movements through space and time. So to say that you have an appointment to be at the doctor at 1 p.m. on Friday can be reinterpreted in a more detailed way like follows. So watches and such that we have on our wrists are just reliable measuring instruments that have a clock pointer or a digital counter. And we are able to assign synchronized events to each other in time and space by all having watches that operate in the same kind of reliable way that we can then assign events in synchronicity with the indications shown on the watch. So if you're supposed to be at the doctor at 1 p.m., you can think about that as, here are two things that should be seen at the same time by the observer. Make it so that the moment when the time shown on the clock face is the indication of 1, that at that point you observe yourself walking through the door of the doctor's office. Okay, so we can assign two events as simultaneous relative to an observer. We just have to have it that there's two light signals that reach that observer at the same moment. But this isn't even the weird part yet, even as strange as this is, thinking about simultaneous in terms of like light signals and an observer positioned intermediately between two events that give off light. It gets a lot weirder right now, because what we're now going to show is that according to this definition, the same two events are not going to be simultaneous relative to another observer in the scene with a different state of motion. Okay, and then once you start to grapple with that possible idea, it's just really, really strange, and it's very interesting. So let me help you with that. Now we're going to add a second observer to the scene, okay? This guy, he's still here. He's still there right there, standing still at M. Staying put, standing still at M. But there's another observer, and this one is on a moving train, okay? So the train is passing through the scene from left to right with a constant velocity v, okay? And there's this guy on the train, another observer. So I want you to, so the train is being carried along the railway with this velocity towards B, away from A. I want you to imagine the following, that this guy, as he's moving with the train, he's going to pass by the midpoint, but he's going to see the midpoint from his vantage point on the moving vessel of the train. So let's call that M prime, just to distinguish it from M. Now, the plane where M prime and M lie is the same plane vertically. Okay, so imagine that he's moving along, and he hits that point M prime. Okay, now, if this was like a video playing through on like YouTube or something, I just want you to imagine that I hit pause right when he's touching that midpoint as he's moving along with the train. I hit pause just so that we can stop the video and think about what we will next see. So right now it's like we hit pause, it was played through, it's continuous motion, but we just want to look at this one part of the sequence. Tell me, when I hit the pause button, is he in alignment along the same plane where the other stationary observer is? So is the second observer aligned with the first one for that split moment that he's hitting the midpoint M prime? Are they on the same vertical line? That's the question. The second guy, as he passes through M prime, pause, is he on that same plane? Yes, good, he is. So just keep that like visual. That's where he will be as the train carries him from left to right. Now, let's imagine that while he's there, at that exact moment is when this dude did his observation of A and B. And that's the moment where he saw the two things happen, and in his mind, and well, not in his mind, but according to his positioning, they happened simultaneously. But now, what about the other guy? He's there at M prime while he's standing still at M, doing his observation. But suppose that he starts doing his observation too of the 2 points A and B while he's passing through M prime. Will he see A and B happening simultaneously if he begins to observe at the exact moment that he hits M prime, at the exact moment that the second guy's looking at A and B? Will the second observer see A and B happening simultaneously or not? And if not, question, which will he see happening first? Okay, Rachel, good. You're saying he won't see them simultaneously, right? But if you can think of all the little elements of our explanation here, yes, it's B that he sees first. Correct, Rachel? But I see a little hesitation because you add a question mark. Same, Andrea. So let's get that clarified so that there's no ambiguity or difficulty at all. Why is it that he does see B first? Yes. In his experience, they're non-simultaneous. It's B first, and then after that, a moment later, it's A. Because the train is moving, Andrea, yes. Say more. Since the train is moving, why does that cause him to see B before A? Unlike our other observer who does see them happening at once. Yes, good, because he's got velocity. And this constant state of motion, V, is carrying him closer to B, further from A. So remember how vision works. Vision works by your eye catching the light signal emitted from the origin point. Well, in this case, there's an asymmetrical distance for the two light signals to travel to reach him. He's like a moving target, basically, and he's running away from A and towards B. So while he passes this midpoint, he's shortening the distance that the light from B has to travel to reach him and his visual system. And he's increasing a larger gap between himself and the light signal emitted from A. So though he sees them as though they're simultaneous, the second observer sees B and later after that A because of his state of motion, running away from the leftmost light signal and towards the right one. So even though they were like perfectly aligned for that moment, he stands still and remains at rest. But he's in constant motion. So the moment that I hit unpause or play on the video, he's getting carried with the train over towards the right. So he has the reference frame of the moving train, and he shares its state of velocity. This other observer has the reference frame of being stationary off to the side of the railway embankment. And they're going to perceive the two events differently because of their different positions and their different state of motion. Now that's very, very strange, because at first you're just hearing that and you're like, okay, well, whatever. It's like an optical illusion or something, but that's not the right understanding. Let me really drill that home. I'm telling you in advance, it's like a trick question, so keep that in mind. So here's my trick question for you guys. You've seen the description of the two observers, so tell me, are the two lightning strikes simultaneous or not? What's the answer to that? Are A and B simultaneous, or are they not simultaneous? What's the answer? You're saying they're not simultaneous, Rachel? Wrong answer. You're saying yes, Ronald? Also, that's the wrong answer. So there's a different answer, and it's not yes and it's not no. Are they simultaneous or are they not? Okay, good, Andrea, exactly. What's the word for that? To the first observer, they are simultaneous. To the second, they're not. It depends on the person. In other words, it's starts with R. Anybody? It's relative. It's relative. It's relativity. This is the theory of relativity. So to this observer, as they're positioned, the two events are seen as simultaneous. In the other observer's frame of reference, they're not simultaneous. Now, you may be a person sitting there hearing me say that, and your mind is refusing to accept this. So you're like, that can't be the case. They're either simultaneous or they're not. So one of them's correct and the other one's just wrong. So maybe the guy who's moving is wrong, you're thinking, because he's moving, and that means that he's seeing like something that's not really real because the state of motion produces this illusion. That's not correct. That's the wrong understanding. Time is relative itself. So for a fact, all we can say is that the two events to observer A relative to, well, to the first observer, I didn't label him A, but to the first observer, they're relative simultaneous. Relative to the second observer, they're non-simultaneous. Neither of the two can claim to be the correct observer with the correct vantage point to observe the events. Now you might think, oh, because he's standing still, he's seeing the real thing. And he's in motion, so it's like an illusion. But no, because even the concept of being motionless is relative. Everything in space is all in motion all the time. You may be thinking that you're sitting still right now, but think again, you're on the surface of the Earth and you're actually being carried around with the whole Earth at huge speeds as it orbits the sun, as it goes in its big elliptical orbit around the sun every year. So everything's in motion. We can only define a thing as motionless with reference and comparison to something else that has a different state of motion. So you may feel that you're at rest, but this guy's just as much a moving object as anything else is. So there's no tie-breaking factor which gives us the answer that, oh, he's got the right vantage point to observe. No, he does. So it's just very, very deep. Here's what it starts to imply. If you think more deeply about it, you'll see this, that all the events of time and space, including the events that you right now think they're not real because they haven't happened yet because they're in the future, they're all real. All the events of space and time are real, and they're all susceptible to observation by a possible observer somewhere in space-time. And how strange is that? It starts to really tear away at the whole idea of human free will. Because if everything that ever is going to happen to you is already something that exists in the framework of space-time, then there's no choices or actions that you could take that would ever be counterfactual to the actual sequence of events that's fully laid out in space-time. Let me make this clear. To this guy, as he's traveling on the train, and due to his velocity, sees B, and then just a subsequent moment later, A, in the order of his experience, B happens in the now, presently, and A is off in the future. But let me add a third observer to show you even how much stranger it can get. Let's suppose we have a third observer in this scenario who's going the opposite direction. Okay? So his train is on another track going from B towards A with velocity V. And suppose that as he passes through the same plane, we'll call it M double prime, relative to his state of motion. Well, if these two things fall into alignment as they pass by each other at the same point that this guy does his observation, then what will the top observer, the third one, see? he'll see which event happened first before the other one, and for the same reason, just in the opposite direction. The third observer will see A occur first, and then afterwards B. And again, it is because of the state of velocity that he has relative to the observed events and other observers that are on the scene. So it's just so strange, because take A and B. These are two lightning strikes. It looks like we have three different answers to what the sequence of events was. Relative to one observer, they happened at the same time. Relative to another observer, B happened first, and then afterward A. And then to a third observer, A happens first, and only after that, B. So the sequence of events is totally jumbled up. It means that A and B don't have any objective linear ordering, that depending on the observer, they happen either at the same time, or one first or the other one first. And that means that the linear sequence of events that you take to be such a strong objective fact about reality, like first you were a little baby, now you're this young adult, then later you'll be this older person that gets married, has kids, whatever. You're thinking that that means that is unchangeable, that is absolutely fixed, and the sequence is set down and it's a fact. But now what you're hearing and learning from Einstein is that that's not true, that there is another possible description of the sequence which has them going in different order or even at the same time. So it's very, very strange. That means you have to grant actual objective reality to moments that relative to you appear to be in your personal future. So how strange is that? Like whatever you're going to do in 10 years, it's already something that exists in the universe. And the past that sometimes you think is gone forever, and it's just there's only the present. The past is gone, the future is yet to be. This Einstein theory of relativity forces us to embrace a concept called eternalism instead of presentism, which means that it's not just the present that exists, it's all the moments, including the full future stretched out throughout all of time and space. So this simple little thought experiment is actually delivering very, very far-reaching, deep, puzzling insights. I want to go a little further with this and explain some additional things about the theory of relativity and how it really starts to further erode our common sense idea of time. Next, I want to talk to you about the concept of time dilation, and the best way to explain that is through the concept of what's called a light clock, okay? Before I do that, though, get to the light clock example, I'm going to read you the Einstein explanation of what we have just said. And one thing that's great about Einstein, many people have not actually read him, but I think that he's one of the clearest writers in history. I mean, he just says the stuff so blunt and clear. He brings things down to earth pretty well for such an intelligent mind. So he says, up till now, our considerations have been referred to a particular body of reference, which we have called the railway embankment. We suppose a very long train traveling along the rails with constant velocity v, and in the direction indicated in the graph below. People traveling in the train will use the train as a reference body. They regard all events in reference to the train. So they're moving with the train, and so for them, that's their state of motion too. So every event which takes place along the line also takes place at a particular point of the train. Also, the definition of simultaneity can be given relative to the train in exactly the same way as with respect to the embankment. So as a natural consequence, the following question arises. Are two events, the two strikes of lightning, A and B, which are simultaneous with respect to the railway embankment, also simultaneous relative to the train? We will show now that the answer must be in the negative. In other words, the answer must be no. They're not going to be simultaneous to the other observer. When we say that the lightning strikes A and B are simultaneous with respect to the embankment, we mean this. The rays of light emitted at the places A and B where the lightning occurs meet each other at the midpoint M of the length AB of the embankment. But the events A and B also correspond to positions A and B on the train. Let M prime be the midpoint of the distance A to B on the traveling train. Just when the flashes of lightning occur, this point, M prime, naturally coincides with the point M, but it moves towards the right with the velocity v of the train. If an observer sitting in the position M prime in the train did not possess this velocity, then he would remain permanently at M, and the light rays emitted by the flashes A and B would reach him simultaneously. They would meet where he is standing. But in reality, he is hastening towards the beam of light coming from B, whilst he is riding on ahead of the beam of light coming from A. Therefore, the observer will see the beam of light emitted from B earlier than he will see that emitted from A. Observers who take the railway train as their reference point must therefore come to the conclusion that the lightning flash B took place earlier than the lightning flash A, and we thus arrive at the important result. Events which are simultaneous with reference to the embankment are not simultaneous with respect to the train, and vice versa. Every reference body has its own particular time. Unless we are told the reference body to which the statement of time refers, there is no meaning in a statement of the time of an event. Before the theory of relativity, it was always assumed in physics that the statement of time had an absolute meaning, that it is independent of the state of motion of the body of reference. But we have now seen that this assumption is not compatible with the definition of simultaneity. So that's Einstein's description of it in his words. To extend this theory a little further, and for you guys to understand some of the other very puzzling and deep consequences that it does have, I want to talk next about time dilation and, if we can get there, the twins paradox. Okay, so here we go, time dilation. One of the weirdest things about the theory of relativity is that depending on how fast an observer is moving, or an object is moving, it can pass through time slower or faster than another object or another observer who has a different state of motion. The basic rule is that the faster moving object passes through time slower relative to those that are at a lesser state of velocity or that are at rest. To showcase this, we got to use this example of a light clock. Okay, so here is a light clock. It's just two planes of mirrored glass. Okay, so that's what you got to pretend these are. This is like a surface with a mirrored surface, so it's reflective, and so is that. So it's like two mirrors set up like so. Let's take a photon of light, and let's excite the photon and fire it towards this top surface. Now, since this is mirrored, it reflects light, and it will reflect the photon and bounce it right back down. So the photon then goes back down, and since this is a reflective surface, it bounces the photon back up. So now we have this bouncing photon coming up and down between the two planes, like that, okay? And now we're going to convert that into a time measurement device, like a clock, so that since there's consistency to the velocity of light, let's just suppose that with each cycle touching the top to bottom is a 1 second interval of time. 1, 2, 3, okay? So it's going like that. That's the light clock. Let's take an observer now, and let's put this observer here with the light clock. So they're able to observe it. As they're seeing the light clock, this light clock is just standing still right in front of them. It has no velocity. So the observer and the light clock are both standing still. They're motionless. But the light clock appears to have this angle of approach for the photon. It's vertical. It's just straight up and down. But now I want to imagine that we take a second light clock. Okay. Here's the second one. And in the second one, we also have a photon dancing back and forth, up and down. But here's what we're going to do to this guy here, the top light clock. Let's take it, and we're going to accelerate it very fast to the right with a high speed, velocity v. Maybe that speed is something close even to the speed of light, but whatever, it's a high speed. It's a very, very fast speed. So this one stays at rest with our motionless observer. These guys stay still. They stay put. But this one up here, we take it, and we accelerate it far off to the right very fast. Before we sent it to the right with that velocity, these two were in perfect unison. The top light clock and the bottom light clock are like twins. So they were just both bouncing up and down like that. And let's imagine that they were issued from the assembly line at the same moment. So these are like two twin light clocks of the exact same age. And they've recorded the exact same number of seconds and stuff, right? Now suppose that this one's getting accelerated to the right and this one stands still. I need you to really try to get into some like mental gymnastics with me and visualize something in your mind's eye, all right? What do you think would be the trajectory shown to this observer of this photon in the light clock once it starts accelerating quickly to the right? Will the angle of approach that it takes as it cycles from top to bottom still appear to be vertical? Or if not, can you tell me how the angle of approach might appear visually different to this observer as he continues to remain standing still, but looks at the top light clock zooming off to the right? I'm just asking you, like, what would be the visual that he would see of the photon's angle of approach to the top and bottom? It will now appear zigzagged. That is correct. It will be elongated, yes, Ronald, but in particular, it'll be on a diagonal because as it's being carried to the right, it now sort of describes an angled trajectory like a streak. And the faster that it's going, the more elongated will the approach for each cycle appear to take. So it basically has to traverse a longer, wider angle to complete the one cycle of touching top to touching the bottom, as seen from this observer. Now, if this observer was riding along with the light clock, okay, and he shared its state of motion, what would he see? Would he still see it going vertically if he was moving along with it, or would he see that diagonal thing? That's a question for you. If he is traveling with the light clock, does it see like it's going straight up and down, or does it still look diagonal? I'm just varying the example a little bit. In one way I've described, he's standing still while it moves. If he's with it, yeah, it just looks vertical, because now there's no differential between the moving object and him. So his eye just tracks it as it goes straight up and down right in front of it, as it appears to be standing still, but of course he's moving with it, okay? Now, question. If this guy remains at rest with this light clock, while the other one has been accelerated very quickly, suppose we allow it to go really, really fast off to the right, and we allow it to, like, I don't know, orbit the Earth many times, traveling at that 90% of the speed of light or something. Then finally we allow it to come back and reunite to the first light clock, and it comes back and it returns to a state of rest. So now they're both back together, but the top one has done a lot of fast speed travel. Which of the two light clocks, after that first one has moved that fast and come back to the second one, which of the two will now have more seconds recorded on it? The one that was at rest or the one that was moving fast? Which of the two will now have more elapsed cycles? No. So let's try again. Which has more seconds that have passed? First is a bit ambiguous. Do you mean the motionless one or the one that is in motion? There's first in the order of my description, and there's also first in the order of like vertical top to bottom. So yes, the one that is at rest will have counted off more seconds. But I see that you're trying to guess. Well, you shouldn't have to guess. Why is it abundantly clear if you just think about the visualization that you should have in your mind? Why is it that the one at rest is counting off more seconds while this one takes longer to count those seconds? Because, okay, here's this guy standing still. The path of motion that the motionless one takes is straight up and down vertical. That's just less space to complete a cycle. The one that's moving fast, because of the long elongated angle of approach, appears to take a longer pathway to complete a single cycle. So the one at rest bounces more often because it has less or no velocity. Yes, exactly, Ronald. So when they're reunited, this is so strange. They started off, I told you, as the same age, coming out of the assembly line at the same time. But now, because one of them has moved fast while the other one has stayed at rest, it has taken less time than this one has. So the motionless light clock is now actually older than its twin, even though they were like born on the same day. That's so strange. It's not a distortion that can be just written off because one of the light clocks is properly functioning and the other is improperly functioning. It is time itself that has flowed at different rates for the fast-moving clock as opposed to the slow one. Now, how weird is that? We usually think that time moves at a constant rate, and it's always the same for everybody. 1 hour is an hour, and it's not like if I go through an hour, you're going through 2, or you're going through 3, or a year. But the theory of relativity shows us that, in fact, if things can achieve variable speeds of a significant difference like this, then we would see time dilation. And in fact, there is time dilation even in our everyday lives, but it's just happening on a minuscule infinitesimal scale. Let me go a little bit further with this example of time dilation. And now that you understand the light clock example, at least a little bit, we're going to talk about what's called the twins paradox. And this is like a very fun and weird example from physics. So, twins paradox. Okay, so suppose you have a pair of identical twins. Now, one thing that we all know about identical twins is that those are people who are like the same age. They're born, roughly at the same time. And my own siblings, my 2 brothers and my sister, they're triplets. So, I know all about the twins and so on. But take a case of identical twins. They're the same age. They have the same birthday. Okay. Yes, Andrea, this is it. So, but let's not have a big spoiler just yet. Let me get there. So take these two twins, right? And let's put one of them in a rocket. And let's send them out into space going at really fast hyperspeeds, okay? Traveling around interstellar space. The other one, let's keep on the planet Earth remaining in a relative state of rest, okay? Now, after one has traveled really fast through space in the shuttle, space shuttle, and they come back down, which of the two is going to be older? The one that stayed on the planet Earth at rest, or the one that was moving around through space quickly? Now these two people are the two light clocks. And I'm asking you, if one has made a lot of travel at that high velocity and returned back, then what will we see? That the one on Earth is now older, yes, than the one who was traveling fast. So the basic rule is moving fast through space, velocity-wise, makes you move slower through time, temporal-wise, relative to other observers that are not moving at the same velocity as you. How weird would that be, okay? And it would depend on how fast the person was moving and for how long. So if the person's moving at like a significant percentage of the speed of light, then depending on how long they're doing that, there's going to be more and more time dilation. So it could be a situation where they get in the ship, they're flying around close to the speed of light, and they do that for like, relative to them, 8 hours. They come back and touch down on Earth, and it's been like a year or 10 years to their identical twin. Now, how weird would that be, to have an identical twin brother or sister, and now they're like 10 years older than you? And the reason they're older than you is because you've been moving through space faster, so time has been literally flowing slower for you than for them, relatively speaking. It seems like it's not supposed to work that way. Like what we've always thought, or what we usually just take as a common sense idea, is that it's not possible for more time to pass for me than for you. I mean, there's just one time frame, and we all go through it at the same rate. But Einstein's theory of relativity shows us that space and time are so inextricably woven together that the rate of velocity that you have does, in fact, change the rate of time's passage. So we actually all have our own personal time frames depending on our current state of velocity. Now, next question. If this is true, and by the way, this is not just speculated on, this is actually something that has been scientifically proven. So if you want to know how has this been demonstrated through evidence, there have been real experiments. So in Einstein's own time, they were able to take one clock that they had the ability to measure time way out to like 100 decimals, like tiny nanoseconds, and they would take two of these, place one of them in like a jet that's able to go not the speed of light or anything close to it, but as fast as these jets can go, like several times the speed of sound. And then we reunite it after having traveled around the Earth, back with its twin clock, and the exact amount of time dilation predicted mathematically by the theory was the result shown when the two clocks were reunited. Another example of how this has been proven. We don't have the ability to teleport, well, I shouldn't say teleport, a whole different concept, but we don't have the ability to achieve these kind of massive velocities with a human body. First of all, because we don't have the technological means to accelerate massive objects that fast, like the fastest things that we can travel around in is like the space shuttle, which when it gets fully up to speed out of outer space, it's like 8 miles per second. But the speed of light is 186,000 miles per second, so it's orders of magnitude greater. So we're not going to get a human being traveling that fast, it doesn't seem. But what we can do, and what we have done, is accelerate tiny little elementary particles in these giant particle accelerators, like over in Europe. And we can get them going very close to the speed of light, over 90% of the speed of light. So when we do that, the half-life of these elementary particles is dilated, and it extends and it lasts for longer than another particle that's not placed in that chamber. And so there's real proof, basically, of time dilation. So, question to you. If time dilation is real, then how come we don't experience it or observe it in our lives? How come, for example, people that fly around and take a lot of plane rides are not aging way slower than everybody on the surface of the Earth who just stays at home on the couch? Or how come people that don't run a lot all the time, like me, or just drive really fast on the freeway, how come they're not aging slower or going through time less fast than people who are more motionless? How come you think that this doesn't get observed or noticed at all by us if it's something that really exists? What would be your theory or guess about that? If time dilation is real and all it takes is different speeds, how come we don't notice that? How come it's something that we just don't, like I'm going to age way slower than my twin brother or something because I'm more active, moving more. Relative, well, nah, it's a little bit not so substantial of a comment. I mean, just one word. It's hard to infer what you meant by that. But no, not so much. Let's try again. Why do you think that the phenomenon is not noticed or observed if it's real by us humans on the planet Earth? Because sometimes we move at different speeds than each other, so how come this isn't something that we can take note of? It's an easy answer in a way. Just think about it. It's because we're not able to what? Really? I mean, I know this, I don't want to put you guys too much under the gun. I know this is like a smaller group, and I appreciate just the fact that you're here. Yeah, it's not enough of a discrepancy in speeds, exactly, Brooklyn. For this to be something that would really be measurable and noticeable on more than the microscopic scale, we would have to be able to achieve variable speeds of a significant magnitude. Like I would have to be able to go like 50% of the speed of light while you're standing still. But even the fastest modes of transportation that we've been able to invent don't allow us to go fast enough for the effect to be anything more than almost infinitesimal. But look, if we really did have the ability to accelerate our bodies at that speed, then we would have all kinds of problems with our clocks, because some people's clocks would, they'd be going through time at different rates than other people, and we could never, be in sync. But it is the possibility of like future time travel. If you could step into a centrifuge, for example, that could spin you close to the speed of light for a certain amount of time, then you could emerge from that after like 5 minutes of personal time into a world that's like 5-7 years later. So it brings to reality like weird science fictional concepts, like the possibility of time travel into the future. We probably won't ever be able to do that with a human being though, because the forces that you'd be exposed to would just tear you to shreds. But in theory though, it's a theoretically conceivable thing. Last thing I want to say to you guys about the whole light clock thing is this. Another case of a physical phenomenon that is exactly parallel to that is the Doppler effect. Okay, so what is the Doppler effect? It's an auditory phenomenon that happens when you have sound waves coming at you from an object that has a certain state of velocity. Okay, now consider this. If you're driving in a car and you honk the horn, you just hear the horn honk with no modulation in its tone. So you hear right? Now, but what if you're standing still and a car honks as it drives past you? Do you notice the wavering of the tone that the sound appears to have to your ear as you're standing still? Question, how does it modulate? As the car approaches and as it goes farther from you in space, how does the tone change? Does it become higher in pitch or lower in pitch as it does what? Yes, that's why the songs change pitch. Yes, of course. But as it approaches, what happens to the tone? Does it become higher in frequency or lower? And as it goes away from you, does it become higher in frequency or lower? Okay, higher pitch corresponds to which part of my question, Sierra? The higher pitch is when it is the car that is, higher as it approaches, lower as it goes farther away. Not just louder. We're talking about like pitch, like versus like high versus low. Okay, so as the horn is approaching you with that velocity, it actually scrunches the amplitude of the sound wave. So it makes it a more spiky set of peaks and troughs in the amplitude of the sound wave that strikes your ear. And that causes the effect of it having a higher pitch. As it goes farther away from you, the distance between your ear and the moving object that emits the sound wave creates a longer and more stretched out amplitude and trough, which produces a lower signal, a lower tone. So that's why if it was music or a horn or anything, you would hear the tone vary. It'd be like, eeeew. But if you're in the car, you don't hear eeew. You just hear ee because you're moving with it, and so the sound waves don't have the modulation that occurs from changing your distance between the source of the sound signal and your ears. So light propagates as a particle and as a wave. The wave-like properties of light are what account for this dilation effect that is observed in the light clock example. So the same way that the fast-moving light clock starts to have a more angled and gradual approach for each cycle is the same kind of phenomenon that happens with sound waves as the object's being stretched further away from you. So that's just another corollary to the physics that we're trying to explain here. I'm a big fan of Einstein, just to tell you guys. I mean, growing up, one of my parents was an aerospace engineer and working for the U.S. Defense Department, building all these defense satellites and missile shields against whatever enemies might attack us. And Einstein's theory of relativity is actually a very important part of the technologies that are used to develop global satellites and missile defense systems. So I was always kind of given a sense of respect for science and physics as a young child. And I think that where contemporary science and then philosophy kind of meet is in this interesting work of Einstein and the other cutting edge physicists, and also quantum physics, which is a whole other can of worms that we're not going to really talk about. So I kind of like the ability to have this in the class, and I think it's great that our book is willing to bring a couple of disciplines together so that we can think of those things as we study philosophy. The sound wave frequency thing is like, yes, it's a case of the Doppler effect. That's right. Yes, Andrea. And you can read about that and see the connection that such an example could have to the light clocks sort of thing. Andrea, you said that you watched that video. If you did watch the whole thing, then there is a sequence in it where they have a surfer and he's on waves, and they try and explain to you the wave-like properties of light that account for some of the things that I'm saying. So I think you said it would cost $1 or whatever. I would never tell students, you have to pay $1 to watch something. But if you do have a little time and some attention to spare, and $1 if that's the case, then I would recommend watching that video, because it brings a lot of, I think, reinforcement to the lesson here, which, I mean, this is a real crash course in physics, right? We've been talking for an hour, and you're learning some of the biggest important issues in the last century in physics, and the physics of light and electrodynamics of moving bodies. Okay, guys, so that's what I wanted to talk to you about today. We have another lesson on time that's scheduled for Tuesday, so we'll try and speak a little bit more about some of these cool concepts then. Would it really be possible for the backflow as long as someone runs faster than light velocity? No, there's no way to achieve a speed that goes beyond the speed of light. It's the maximum physical speed, because light is the carrier of all information. So no, there is no possible way to go beyond the speed of light. But could one person go, you mean back in time? Is that what you're asking? It's considered to be theoretically conceivable if you could warp time and space in such an aggressive way, like the singularity at the back of a black hole. Sometimes people think that could create such physical forces as to allow an object that passes through it to go to a different point in time-space. But of course, the human body could never survive the travel into a black hole, so it would be a mystery to us. Yeah, only Barry Allen could do it. It's funny. There's a lot of good fiction out there when it comes to science fiction stories of time travel. If you guys ever have any recommendations for me, I'm always looking for those. Someone said Steins Gate was a show that dealt with time travel the other day and that it was pretty good. I don't know. There's a really good film that I used to show in this class when we had in-person meetings, when we had a little free time, and it was on the subject of time, called Time Crimes. It's actually a Spanish film with either subtitles or dubbed. But Los Cronocrímenes is a great movie. It's one of my favorite of all time. So if you ever have a chance, that's a great entry into the time travel genre. Okay, guys. Well, thanks again for being here. And like I've said, I know we have a kind of a core group that comes pretty reliably. I figured that the time schedule, 5:30 to 6:45, and with the pandemic and everything else, and I'm not like a stickler for, enforcing any of these rules, but just, I would insist that if you really want to do well, you should try your best to attend as reliably as possible, because, it's your grade, and it's not so easy to just learn these things playing catch up after the fact. So, people will do what they want to do, but I always appreciate your guys' attendance, and when you're here, it just makes it a lot better. But thanks again, everyone. Okay, have a good weekend. Be in touch with me. If you have any questions about any grades from anything earlier, please send me an email. Don't worry that emails are getting lost. If that happened last week, I really can't speak to that and don't know exactly why. But I would suppose, because I had a lot of problems with it, that during the election, a lot of people are online, and it seemed like it was overloading some of the servers. Okay, guys, then see you next time. Thanks again.